What if the greatest obstacle between humanity and the stars is not distance, technology, or even time, but the laws of physics themselves? Imagine that tomorrow astronomers discover something extraordinary orbiting Proxima Centauri, the nearest star beyond our sun. Not just another rocky planet, not just water. They detect unmistakable evidence of an advanced civilization, cities glowing on the night side, artificial structures in orbit, perhaps even signals deliberately aimed toward Earth. For the first time in human history, we would know we are not alone. There would be only one problem. They would be more than 4 light years away. That sounds close on a cosmic map. Yet with spacecraft technology, anything like what humanity possesses today, reaching them would take thousands, perhaps tens of thousands of years. So we would immediately begin asking the question science fiction has trained us to ask: how do we build something faster, a more powerful engine, a fusion spacecraft, antimatter propulsion, a laser-driven sail? Eventually, perhaps something capable of approaching the speed of light. But the deeper physics becomes, the stranger the problem gets, because nature does not merely make interstellar travel difficult. At extreme speeds, nature seems to construct barriers around it. Energy requirements explode. Collisions with microscopic particles become dangerous. Radiation becomes increasingly severe. Time itself stops behaving the way our intuition expects. And above everything stands one number that modern physics refuses to let ordinary matter cross: 299,792,458 meters per second, the speed of light. To understand why this number matters so much, we have to return to one of the strangest revolutions in the history of science. Before Einstein, space and time were treated almost like an invisible stage. Objects moved across space, while clocks measured time independently in the background. If a train moved at 50 miles per hour and someone inside threw a ball forward at 10 miles per hour, a person standing beside the tracks would see the ball moving at roughly 60. Velocities added. Simple. Then light ruined everything. Experiments suggested that no matter how an observer moved, light in a vacuum was measured traveling at the same speed. Einstein took that strange fact seriously. In 1905, special relativity transformed our understanding of reality. Space and time were no longer separate absolutes. They became parts of a single structure, spacetime, and measurements of distance and duration depended on motion. The speed of light was not merely the speed at which light happened to travel. It became something far deeper, a fundamental limit built into the geometry of spacetime. And that creates our first enormous problem. Suppose you build a spacecraft and accelerate it faster and faster. At 10% of light speed, relativity matters, but not dramatically for everyday intuition. At 50%, the effects become harder to ignore. At 90%, they become substantial. Push toward 99%, 99. 9%, 99. 999%, and something extraordinary happens. Every additional step toward light speed demands disproportionately more energy, not because the spacecraft suddenly develops some mysterious resistance from space. The mathematics of relativity itself changes the relationship between velocity, momentum, and energy. For an object with mass, reaching exactly the speed of light would require unbounded energy. No matter how powerful your engine becomes, the final gap never closes. You can approach light speed. You cannot reach it. And you cannot accelerate an ordinary massive spacecraft through it. This is not simply an engineering problem waiting for a clever inventor. Within special relativity, it is a fundamental physical restriction. Leonard Susskind has spent much of his career exploring precisely these kinds of boundaries. The places where ordinary intuition fails and the underlying structure of physics becomes impossible to ignore. His work spans quantum field theory, string theory, black holes, information, and the foundations of modern theoretical physics. And one theme appears again and again in that world: nature is under no obligation to behave according to human expectations. The universe is not designed around our desire to cross it. But perhaps we do not need to reach the speed of light. Proxima Centauri is about 24 light-years away. If we somehow built a spacecraft capable of cruising at a significant fraction of light speed, suddenly interstellar travel begins to sound imaginable. At 10% of light speed, ignoring acceleration and deceleration, the journey would take a little over 40 years as measured from Earth. At 50%, less than 9 years. At 90%, under 5 years in Earth's frame. That sounds almost reasonable. Until you ask the question every real spacecraft engineer must ask: where does the energy come from? A spacecraft moving at relativistic speed carries an enormous amount of kinetic energy. Even a relatively small vehicle accelerated to a large fraction of light speed would require energy on a scale far beyond ordinary transportation systems. And then you have to slow down. A spacecraft arriving at another star at 90% of light speed without a way to decelerate has not completed a journey. It has performed a flyby. So unless the destination already contains infrastructure capable of stopping you, your propulsion system may need to solve the energy problem twice. Then there is the fuel. Traditional rockets carry propellant, but carrying propellant increases mass, which requires more energy, which can require more propellant. For interstellar missions, this can become brutally restrictive. Nuclear fusion has long been considered one possible route beyond chemical rockets. Antimatter is even more energetic in principle, because matter-antimatter annihilation can convert rest mass into other forms of energy with extraordinary efficiency. But producing, storing, and safely using macroscopic quantities of antimatter is far beyond present engineering capability. And even an almost perfect energy source does not repeal relativity. It only helps you approach its limits. Perhaps, then, the spacecraft should carry almost nothing. Instead, leave the engine behind. That is the logic behind concepts such as laser-driven light sails. Powerful lasers could accelerate an extremely lightweight sail from afar, potentially pushing tiny probes to a substantial fraction of light speed. Projects inspired by this idea have seriously investigated whether gram-scale spacecraft might someday reach nearby stars within decades. That is real scientific and engineering research. But notice what happened. To make interstellar travel more plausible, we shrank the travelers from human beings to tiny robotic probes. The stars may be reachable by machines long before they are reachable by us. And even those machines face another enemy. Space looks empty. It is not. Between the stars lie atoms, ions, dust grains, photons, magnetic fields, and cosmic rays. The interstellar medium is extraordinarily thin by terrestrial standards, but a relativistic spacecraft crosses enormous distances. At ordinary speed, hitting a tiny dust particle is insignificant. At a large fraction of light speed, the situation changes. Kinetic energy rises dramatically. In the spacecraft's frame, incoming particles can become high-energy radiation hazards. Shielding becomes essential, but shielding adds mass. More mass requires more energy. More energy creates more engineering difficulty. The faster you try to travel, the more hostile the apparently empty universe becomes. There is an almost cruel elegance to it. Speed solves the problem of travel time while creating new problems that grow because of the speed itself. But relativity also offers something astonishing in return. Suppose you could build a spacecraft capable of traveling extremely close to light speed. People on Earth might watch decades or centuries pass during a sufficiently long journey. The travelers would not necessarily experience the same amount of time. This is time dilation. From Earth's perspective, a rapidly moving clock runs slow. From the traveler's perspective, their own clocks behave normally, while distances along the direction of travel are length contracted. These are not optical illusions. Relativistic time dilation has been experimentally confirmed. Precision clocks, particle accelerators, and satellite systems all reveal consequences of relativity. So in principle, travelers moving sufficiently close to light speed could cross enormous distances while experiencing much less time than observers remaining on Earth. Suddenly, a strange possibility appears. Maybe relativity does not make deep interstellar travel impossible for the traveler. Maybe it makes returning to the world you knew impossible. Imagine leaving Earth aboard a ship capable of extraordinary acceleration and relativistic cruising speeds. For you, perhaps only a few years pass. You explore a distant region and return. But Earth has experienced far more time. Everyone you knew could be old. Depending on the journey, entire generations could have vanished. Traveling near light speed would not merely move you through space. It could separate you from your own era. The price of reaching the stars might be exile in time. And this leads to a deeper issue. Human civilization thinks about exploration using the logic of ships. Columbus crossed the Atlantic and returned. Aircraft cross continents in hours. Astronauts travel to orbit and come home. We imagine interstellar spacecraft as larger versions of the same idea. But cosmic distances may demand a completely different concept of travel. Perhaps an interstellar mission is not a voyage. Perhaps it is permanent migration. A generation ship could move far more slowly than light, while carrying a self-sustaining population whose descendants eventually reach another star. No law of known physics clearly forbids such a vessel. But now the challenge changes from propulsion to civilization. Could a closed ecosystem survive for centuries? Could a population remain genetically healthy? Could machinery be maintained across generations? Could political institutions survive inside a spacecraft from which nobody can escape? Would the descendants of the original crew even care about the destination selected by ancestors they never met? Physics might permit the journey while human nature destroys it. So perhaps we need another shortcut, a wormhole. General relativity allows space-time to curve. Matter and energy shape that curvature, and the curvature tells matter how to move. This immediately suggests a seductive idea. If two distant regions of space could somehow be connected through a shortcut in space-time, a traveler might cross between them without locally moving faster than light. The concept appears in theoretical physics, not merely science fiction. Certain solutions of Einstein's equations contain structures related to wormholes. But mathematical permission is not the same thing as physical existence. Traversable wormholes generally require highly unusual conditions, often involving forms of negative energy or exotic stress energy configurations. Quantum theory can produce limited situations involving negative energy density, but nothing remotely demonstrates that humans could accumulate and control what would be needed to construct a stable, macroscopic interstellar wormhole. And wormholes create another disturbing issue: causality. Under some arrangements, a traversable wormhole could potentially be associated with closed time-like curves, paths through space-time that raise the possibility of returning to one's own past. Once time travel enters the equations, paradoxes appear. Could you prevent your own departure? Could information appear without ever being created? Could cause occur after effect? Physicists do not have a complete experimentally established theory describing what ultimately happens in every such hypothetical situation. Perhaps quantum effects destroy would-be time machines. Perhaps deeper laws preserve causality. Perhaps traversable wormholes simply cannot exist. We do not know. Then there is the famous warp drive. In 1994, physicist Miguel Alcubierre showed that general relativity admits a mathematical space-time geometry in which a region could, in a particular sense, move effectively faster than light relative to distant observers. The idea is often described as contracting space ahead of a craft and expanding it behind. Inside the bubble, the spacecraft would not locally violate the speed of light. It sounds like the ultimate loophole, but the original proposal requires exotic energy conditions, including negative energy densities, and enormous theoretical difficulties remain. Later research has explored modifications and related geometries, but no experimentally demonstrated mechanism exists for creating and controlling a practical warp bubble. There is an important distinction here. The equations of general relativity allowing a mathematical geometry does not mean nature provides a physical machine capable of producing it. Physics is filled with mathematically interesting solutions that may never correspond to constructible objects. And this is where the lessons of thinkers like Susskind become especially important. Modern theoretical physics teaches caution whenever gravity, quantum mechanics, information, and extreme space-time geometry collide. Our two greatest frameworks, general relativity and quantum mechanics, are extraordinarily successful within their domains. Yet they do not form a complete theory of quantum gravity. String theory, one of Susskind's major areas of contribution, is among the leading attempts to understand that deeper structure. And string theory itself produces a strange change in perspective. At sufficiently fundamental scales, the universe may not resemble the smooth, continuous world of classical intuition. Particles may emerge from deeper extended objects. Geometry itself may have unexpected relationships to quantum information. In some theories, what happens inside a volume of space can be encoded in a description associated with its boundary. Susskind was one of the central figures in developing the holographic principle, inspired by the mysterious physics of black holes. That principle does not give us a starship, but it teaches something potentially more profound. Space itself may not be as fundamental as it appears. If space-time emerges from deeper quantum structures, perhaps our current understanding of distance is incomplete. That does not mean faster-than-light travel is secretly possible. There is currently no established evidence that quantum gravity provides a usable loophole for interstellar transportation. But it does mean that declaring every future possibility permanently closed would go beyond what science can justify. Our present theories impose powerful restrictions. A deeper theory might explain those restrictions in an entirely new way. History has done this before. Newtonian mechanics once appeared to describe motion universally. Einstein did not show that Newton was useless. He revealed that Newton's laws were an approximation that works extremely well when speeds are low and gravity is weak. Quantum mechanics later revealed another layer of reality that classical physics could not anticipate. Yet every deeper theory must still explain why older successful theories worked where they were tested. Any future theory of quantum gravity will have to recover relativity in the regimes where relativity has already been confirmed. So we should not expect a future discovery simply to erase the speed of light because we find the limit inconvenient. There is another possibility, however, that is rarely as exciting in movies because it removes us from the spacecraft entirely. What if humans are not the things that travel between stars? Machines can tolerate conditions biological organisms cannot. A robotic probe does not need oxygen, food, sleep, or protection from psychological isolation. An advanced autonomous system might travel for centuries. A self-repairing machine could potentially survive journeys no human crew would attempt. Push the idea further. Suppose a civilization becomes capable of transmitting an extremely detailed description of a mind. Could information, rather than biology, become the true interstellar traveler? Even information cannot outrun light, according to known physics. But information does not necessarily care about subjective weighting in the way a biological traveler does. A signal can cross 1,000 light years without needing food or fuel after transmission. Perhaps the cosmic civilization of the future would not consist of biological beings moving physically from world to world. Perhaps it would consist of information spreading at light speed through a network of machines. But then, an uncomfortable question appears. Would the entity reconstructed at the destination actually be you? If every memory, personality trait, preference, fear, and neural pattern were reproduced perfectly, would consciousness continue across the gap? Or would you remain on Earth while a perfect copy opened its eyes beneath another sun, convinced that the journey had succeeded? Physics cannot yet settle that philosophical problem. And suddenly, interstellar travel has led us somewhere unexpected. The deepest obstacle may not simply be building an engine. It may be deciding what counts as traveling. For most of human history, distance was measured by how long a body required to cross it. Modern physics breaks that intuition. Relativity connects distance to time. Quantum theory challenges simple ideas about objects and information. Black hole physics suggests that space-time and information are linked in ways we are still struggling to understand. The universe may permit exploration, but not necessarily in the form we imagine. And there is one final scale that makes all of this even more unsettling. The Milky Way is roughly 100,000 light-years across. Even a light signal requires around 100,000 years to cross it from one side to the other. And the observable universe extends vastly farther. There are galaxies whose present-day distance from us is measured in billions of light-years. Because cosmic expansion is accelerating, some sufficiently distant regions are effectively beyond our future causal reach. Signals we send now will never arrive there, even if they travel at light speed. There are places in the universe that humanity may never touch. Not because we are too primitive, not because our engines are too weak, but because the evolving geometry of the universe places them beyond what we can ever influence. That may be one of the hardest ideas for an exploratory species to accept. We evolved to cross boundaries. A mountain exists, so someone climbs it. An ocean appears, so someone sails across it. The moon hangs above us, so eventually footprints appear in its dust. This history tempts us to believe every frontier is temporary, but the universe does not promise that. Some boundaries may be technological, some may last 1,000 years, and some may be woven into reality itself. Yet this does not make the stars meaningless, it makes them more precious, because somewhere between impossible and merely unimaginably difficult lies the future of human exploration. Tiny laser sails may someday race toward nearby stars. Robotic probes may survive journeys longer than human lifetimes. Future propulsion systems could achieve speeds that would make today's spacecraft look almost motionless. Generations of physicists may discover principles we have not yet imagined. But whatever happens, the universe will set the rules. And perhaps that is the most unsettling lesson hidden inside the dream of interstellar travel. For centuries, we looked at the stars and assumed the challenge was reaching them. Physics asks a different question. What if the stars were never destinations waiting for us at all? What if they are mirrors, showing an intelligent species the boundary between what it can imagine and what reality will actually allow? And if space-time itself is only the surface of something deeper, as some of the ideas surrounding quantum gravity and holography suggest, then perhaps the ultimate question is not whether humanity will ever learn how to cross the distance between the stars. Perhaps it is whether, after finally understanding what space truly is, we will still believe that distance was the right problem to solve.